Finding limits graphically and numerically. Before we can even start finding limits, we need to define what a limit is. So here you can see that a limit is defined as f of x is some function defined on an open interval that contains c, except possibly at x equals c. And we say that the limit as x approaches c of f of x equals L. Now I have these different expressions up here circled in different colored boxes, and that matches up with what we say down here. And a couple more things I want to say about this is if you look at the definition, you say this interval that contains c. And it's also in the actual definition of a limit. C is a specific x value. That is, C is some number that x is trying to get very close to. Likewise, when we look over here in the definition with L, L ends up being a specific y value. So, what's going to end up happening is that we will look at a function and approach a specific x value from the left and the right, as that's how you move in the x direction, left and right. And then we will see if the y values end up being the same number. This is best illustrated on the next slide with graphs. So the easiest way to understand what a limit is and how it works is to look at limits graphically. So we will use the graph to estimate the following limits. F of x is graphed at the right. So this blue graph over here is f of x. Now as we read this first limit here, the limit as x approaches negative 3 of f of x, we are trying to figure out what this limit is equal to. So in reading this limit one more time, the limit as x approaches negative 3, we will look at the graph over here to find where x equals negative 3, and that's right here at this point. So at this point on the graph, and when I refer to the graph, I mean the actual function, not the grid itself. So on the graph, as we approach negative 3, that means something like this. We can approach negative 3 from the left. So as we get closer and closer and closer to negative 3, remember this is a specific x value of negative 3. Our answer needs to be some specific y value. So as this graph travels from the left toward negative 3 as we approach it, it looks like this graph is going to go to the y value of negative 2. And that's good, but from the left is not the only way we can approach a number. We can also approach a number from the right side. So let's do that. As we approach the x value negative 3 from the right side along the graph, it looks like this side of the graph is also trying to send the graph to a y value of negative 2. And it's very important that these match up. So the two sides here, the left side as we approach negative 3 and the right side as we approach negative 3, the y value is giving us a negative 2. So we can use this similar pattern in both of the other, or in all three of the other limits here. So for the second limit, we have the limit as x approaches 5 of f of x, which is the function over here again. So where is 5? 5 looks like it is right here. And remember, we have to approach it from the left and from the right, because there are those two ways to approach an x value. So approaching it from the left, it looks like as we travel along this graph from the left side, as we get really, really close to positive 5, we're trying to get to a y value of 0. And if we approach this x equals 5 from the right side, it looks like the graph is also again trying to give us a y value 0. And since those match up, our answer will be 0. I'm going to give you a few seconds to pause the video so you can try these two other limits by yourself. For the third limit, when you look here, this is the limit as x approaches 0 of f of x. So we need to find the graph and approach an x value of 0. Well, the x value of 0 is right here. So the graph is there when x is 0. So if we approach that graph from the left side, it looks like the y values that we're trying to get to, or the y value we're trying to get to, is 5. And if you approach the graph from the right side of x equals 0, the y value is also getting to 5. With the last limit down here, we have the limit as x approaches negative 7 of f of x. Negative 7 is over here at this dot, or this point, and we can approach this from the left and from the right again. And both of these arrows over here from the left and from the right are trying to get to a y value of positive 2. On this slide, we will be using the graph to estimate the following limits. So again we have f of x graphed at the right, so that's the red graph this time. And you can see that there are some discontinuities in this graph, and that's what changes between the last slide and this slide. And I want to point out very quickly that in green over here, this is a vertical asymptote at x equals 0. So, without further ado, let's take a look at this first limit. The limit as x approaches 9 of f of x. So we need to locate the graph when x equals 9. And that dot would be about right here. So there it is. What we need to do then is approach that 9, that specific x value 9, from the left and from the right. And both from the left and from the right, this graph is approaching the same y value. That y value is 7. And remember, it's very important to be approaching the same y value. So when you take a look at the next example over here, the limit as x approaches negative 4 of f of x, when we approach negative 4, that is right here, when we approach negative 4 along the graph from the left, it looks like the y value this graph is trying to get to is trying to approach is 5. And if you approach negative 4 from the right, this graph is trying to approach a y value of 2. So now we have our very first instance where the left side and the right side are not approaching the same y value. This means the limit does not exist. We write DNE for does not exist. So let's take a look at these last three. In this next one, the limit as x approaches 0 of f of x, we can approach 0 from the left along the graph. So here I am, I'm doing this. It looks like it's trying to approach negative 7. But on the right side, this graph, as we approach 0, is getting closer and closer and closer to positive infinity. And so again, these two quantities do not match up. Infinity is not the same thing as negative 7. So this limit does not exist. So let's take a look very quickly at the next limit, the limit as x approaches 3 of f of x in purple. So as x approaches 3, this means we're traveling along the graph from the left side, and it looks like the graph is trying to approach a y value of -5. And if you approach 3 from the right side, it looks like the y value that the graph is trying to approach is also -5. Now you might be saying, hey, there is a hole in the graph. There's nothing there. This function is not defined there, it's defined up here. Well, this goes back to the definition of a limit. Let f of x be defined on an interval containing c. And then in red text it says, except possibly at x equals c. So that is exactly this case. This function is defined at x equals c, but it's not where we want it to be. It's not at this hole. Regardless, we are trying to find out which y value the function is approaching, not where it is actually defined. So since the graph from the left is approaching -5 y value and is approaching from the right also -5, this means the limit over here will be -5. So if the only discontinuity is a hole in the graph and you're trying to approach that hole, you can still find the limit as if it was a closed dot. And for this last one, I threw this in here just to have fun with some limits. In orange down here, I have the limit as x approaches 100 of f of x. And you might be saying to yourself, this graph over here cuts off at 10. How are we supposed to get all the way over to 100? Well, with this horizontal line, the y values forevermore to the right will all be 7. So if you approach from the left and from the right the x value 100 on a horizontal line, you'll just get whatever value that horizontal line is. So the answer here would be 7. On this slide, I'm going to give you a few seconds so that you can pause the video and try finding these limits based on this graph over here. Good luck. All right, so the first limit we want to look at here is that the limit as x approaches 0. So over here on the graph, as it approaches the x value 0 from the left and from the right, it looks like the graph is trying to approach the same y value from both sides. And that y value is 4. So the limit as x approaches 0 of f of x is 4. In the second example, the limit as x approaches 5 of f of x, over here on the right, as the graph approaches 5, the x value 5 from the left, it looks like it's trying to get to a y value of 7. And as the graph approaches 5 from the right, it's trying to get to a y value of 0. And those do not match. In order for a limit to exist, we need these to match. So since they do not match, this limit does not exist. Next, over here, this limit as x approaches -9. Well, as you approach -9 from the left side, it looks like it's trying to get to that y value of -2. And as you approach, or as the graph approaches, -9 from the right side, it looks like the graph is also approaching a y value of -2. So since from both sides this graph is trying to get to the same y value, is approaching the same y value, we can say that this limit does exist, and the answer is -2. All right, in the fourth limit over here, we have the limit as x approaches -4 of f of x. And so we take a look here as x approaches -4 from the left, and as x approaches -4 from the right. They're definitely not going to the same place. This one is going off to infinity. This one is going off to -infinity. That's not the same thing. So here, just like with the second example, this limit does not exist. In this last one, the limit as x approaches infinity of f of x, well, that's new. You haven't seen that before. But you all know what horizontal asymptotes are, and the graph going off to the right here is going to get very close to the horizontal asymptote but never cross it. The horizontal asymptote is located at y equals -3. So as this graph travels further and further and further and further right, the graph will approach a y value of -3. On this slide, we actually get to see what it's like to estimate limits numerically. So in the smallest number of words, that is finding a limit using a table of values. So we can look at this limit right here, the limit as x approaches 0 of sine of 2x over x, and we want to estimate that limit. So what we can do is we can set up a table that looks something like this, with x and f of x, and we're going to be picking x's of values of x. But before we get to that, I want to make clear some notation here. This f of x refers to what we are taking the limit of. So when we are doing this, we want to have the limit as x approaches 0. So the standard way of doing this is putting 0 in the middle of the table, and then you will pick 3 values to the left and 3 values to the right of 0. And how you want these values to act is that they will get closer and closer to 0. They will approach 0, just like the limit tells you to do. So we will pick -0.1, -0.01, and -0.001. And similarly on the right side, we will pick 0.1, 0.01, and 0.001. So the tables will follow this pattern. As you approach the value from the left, we just get one more decimal place deeper. As we approach the value from the right, we get one more decimal value deeper. So then, to find all of the values that go in this portion of the table, we just have to take these x values and substitute them in for x in our function. And when you do that, you'll get the rest of the table that looks like this. And when you look at these values, as x approaches 0 from the left, down here, these function values, or y values, get closer and closer and closer to 2. And on the right side, as x approaches 0 from the right, these function values get closer and closer and closer to 2. So you can see that as the x values approach 0 from both sides, the y values also approach the same value, and that value ends up being 2. So we can write the limit as x approaches 0 of sine of 2x over x equals 2. So on this slide, we will also estimate a limit numerically. That being said, let's take a look. We have a limit as x approaches -2 of 1 minus cosine of x plus 2 over x plus 2. And again, you want to set up a table, and the table will look something like this. So again, we will have this x and f of x, where f of x is what we're taking the limit of. So again, we want to take that value that x is approaching, this -2, I'm going to put that right in the middle. Now to the left and to the right here is going to look a little differently than it did in the last example. So to the left we will have these three values, -2.1, -2.01, and -2.001. So you can see the number of decimal places increases by 1 every time we are moving along this table. On the right side, you will have three values that look like this, with -1.9, -1.99, and -1.999. So again, these values are getting closer and closer to -2, but this time from the right. So all we have to do now is substitute all of these values in for x, and let's see what happens. These are the values you get. And when you find these values, that is what will take the most time with these types of questions. So when we look at this, the x values from the left are approaching 2. We picked these values so that they approach 2, -2. And the y values seem like they're getting closer and closer and closer to 0. So from the right, the x values are also approaching -2. And we hope that the y values are approaching what we got over here on the left. Let's see what happens. When we approach the x value from the right, the y values get closer and closer to 0. So it looks like as x approaches -2 from the left and from the right, the y values get closer and closer and closer to 0. And that makes us happy. Whenever we find limits and they exist and we can put a numeric answer to it, this 0, that's amazing. We really like that as mathematicians. So we can write the limit as x approaches -2 of 1 minus cosine x plus 2 all over x plus 2 equals 0. For this final example on estimating limits numerically, I'm going to go through and do one example for you, and I want you to try the other one that is not on screen yet for yourself. This limit gets at piecewise functions. So yes, this will be a big part of the first unit in Calculus 1. With this, we need to pick the values from the left and to the right of -3, just like we've done in the previous examples. So you'll set up the table with x and f of x, you'll put the value x is approaching in the middle, and you'll pick some values to the left and to the right that actually approach that specific value. And this piecewise function is where it gets interesting. So as x approaches -3 from the left, we have to substitute these values in to this function up here. This is where x approaches 3 from the left. So when you do that, you'll end up with the following values. -9.3 when you substitute in -3.1, and then subsequently these next two values. So as we approach -3 from the left, it looks like these y values are getting close to -9. Now from the right side of this x value -3, we need to use this middle function, because this middle function is what exists as you approach -3 from the right. So when you substitute these values in for x in this function, x squared, you'll get the following three values. So we have these values now for the function, and it looks like as x approaches -3 from the right, the y values, or the function values, approach +9. And these two numbers are not the same. So we can come up here and write that the limit as x approaches -3 of f of x does not exist. So where you may notice that up here in the piecewise function, this -3 is where the domain of one function stops and the domain of the next function starts. So with that knowledge, you might be thinking, well, the domain of this function stops at 2 and the domain of this function starts at 2. So your task is to pause the video after a few seconds here to find the limit as x approaches 2 of f of x. So you will want to create your table and do things appropriately, pick values, and see what you get for your limit. So hopefully you had a chance to work on this. The table gets set up with x and f of x with the value x is approaching in the middle, so 2 is in the middle. We set up our values 1.9, 1.99, 1.999, 2.1, 2.01, and 2.001. Now as you approach 2 from the left, you'll have to use this purple function up here. So I used purple numbers down here to correspond to that. And as you approach 2 from the left, the y values approach 4. So similarly, we have to substitute these values into the red function up here, and that is because as x approaches 2 from the right, that's this function, the domain is to the right of 2, x is bigger than 2. So when you substitute these numbers in as x approaches 2 from the right, it looks like these numbers are approaching 4 as well. So since we have the same number here, the limit as x approaches 2 of this function here equals 4. With the previous two methods for estimating limits, graphically and numerically, they only just estimate limits. And in order to give you an idea as to why they only estimate limits, we're going to take a look at the following limit. We'll look at estimating the limit as x approaches 0 of sine of pi over x. So first I'm going to do this numerically, and then I will do it graphically on the next slide. But for right now, I'm going to set up a couple different tables just to prove my point. So the first table looks something like this. We have x approaching 0 from the left and x approaching 0 from the right. And when you substitute all of these values in for x in this function here, which I call f of x, you'll get 0 every time. And that leads you to believe that the limit as x approaches 0 should be 0. Well, that is not going to be the case this time. Let me set up a second table to explain why. So in this second table, I picked values like this: -2 over 21, -2 over 201, -2 over 2001, and then the positive versions over here. And I picked these values because when you divide these, it ends up being pretty close to -0.1 or -0.01 or -0.001. So I picked values that were very close to these. But it turns out when you substitute these values in for x up here, you'll get the following values in the function part of the table. So the negative versions of these values give you -1, and the positive versions of these values give you 1s. So now it looks like we have the same exact function up here. I've substituted all these numbers in here for x. That from the left, as x approaches 0, we get -1, and from the right, as x approaches 0, we get +1. So up here, for this limit, we got something that was 0. But for the same exact function, we got something down here that does not exist. And when you create a table of values, it should go to the same, you should get the same result. You should either get 0 every time or does not exist every time. This is perplexing. We'll take a look at what's happening here with getting these two different values on the next slide. So this is the graph of what we just tried to find the limit for on the previous slide. And you can tell that as x approaches 0 from the left and from the right, this graph just goes crazy and oscillates an infinite number of times the closer and closer and closer it gets toward 0. So I could have picked numbers on a table so that as we approached 0, that gave me 1, 1, and 1, and from the left also gave me 1, 1, and 1. Or I could have picked numbers from the left down here to give me -1, -1, -1, and the same thing approaching from the right. So you could make this limit, essentially, if you pick the right values, you could make this limit any number you like. And as I said on the last slide, when you find the limit as x approaches a specific value, it needs to be the same thing every time in order for it to exist. So this leads me to give you 3 behaviors that are normally cause the non-existence of a limit. And these 3 behaviors are f of x approaches different values from the left and right side of C. Go back and look at the graphs of the limits that we did, or the piecewise function that we found numerically to understand that. F of x increases or decreases without bound. We only looked at that in the graph portion, and I'll talk a little bit more about that when we start talking about infinite limits. And f of x oscillates between 2 fixed values as x approaches C. And that is what we talked about right here. It just keeps oscillating between 1 and -1, and we don't know what the limit is supposed to be here. So that's the end of the first lesson. Go forth and conquer the homework.